Hi, my name is Monica Rizzo. I am a rising third-year astronomy grad student at Northwestern University. My advisor is Shane Larson, and today I'm going to be talking about mapping astrophysical parameter space with EMRI Spectroscopy. For those who are familiar with Steve Drasco's work on gravitational spectroscopy, we're sort of riffing off that, but with a different use case in mind. My talk is going to be structured as follows. First, I'll give a brief rundown of what EMRIs are. Then I'll explain how Drasco generates EMRI spectra and identifies spectral features. At this point, I'll motivate our own study and explain how it differs from what Drasco has done. Then I'll explain how we generate our spectra using advanced analytic kludge waveforms. Finally, I'll discuss future directions for and applications of the work we've done. Extreme mass ratio inspirals, or EMRIs, are systems which typically consist of a massive black hole with a smaller, usually stellar mass, companion black hole. As the name suggests, they have very large mass ratios, which means that their dynamics can be well described using perturbative methods. They are also predicted to be Lisa sources, so it's important that we have methods of interpreting and relaying EMRI physics. In the following, the companion black hole is treated as a test mass. So the only astrophysical parameters we really care about are the following: the black hole mass, m, the test mass, mu, the dimensionless black hole spin, a, the inclination angle between the orbital angular momentum and the black hole spin, iota, the test mass orbital eccentricity, e, and the semilattice rectum distance, p. In our study, we're restricting our focus to these four parameters and fixing the component masses. EMRIs, particularly those which are inclined and eccentric, have complicated trajectories. This cartoon represents what typical EMRI orbits look like. These trajectories, though they sometimes appear to be, are not chaotic. If we look at them on adiabatic timescales, where the rates of change of orbital parameters are much smaller than their values, we can start to identify patterns in them and the resulting gravitational radiation. This is essentially what Drasco and Hughes showed in a 2006 publication on gravitational wave snapshots, where they used a perturbative framework to look at EMRI gravitational waves on short timescales. For a given snapshot, they showed that the radiation can be written as what is essentially a mode sum. The radiation frequency at any given time can be broken down into radial, polar, and azimuthal contributions, where mk and n are the corresponding mode numbers. The complex mode amplitudes, h, mk, n, for an arbitrary observer depend on intrinsic parameters, specifically the ones I listed previously. In a 2009 follow-up publication, Drasco derives an expression for the power radiated at a given frequency and uses this to show how mode contributions vary with astrophysical parameters. In a broader sense, he showed that EMRI spectra do have structure, and that structure can be understood in relation to astrophysical parameters. That brings us to how what we're trying to do differs from what Drasco did. Ultimately, our goal is to produce a data product that can be easily interpreted and can be used across the field to understand EMRI science. In our approach, we're starting with a gravitational waveform, looking at a short segment for which the adiabatic approximation holds, and taking a Fourier transform to compute the power spectrum. We then do this over a grid of astrophysical parameters like inclination, black hole spin, etc., and look for trends in spectra. Breaking those steps down further, first we pick a set of initial conditions and use those to compute a 12-hour-long waveform segment. To do this, we use the advanced analytic kludge code, the Git repo for which I've linked below. Then we construct the total strain, h plus minus I h cross, and take its Fourier transform. Here we're showing the power spectrum with a log-scaled y-axis. You can clearly see peaks in the spectrum corresponding to predominant modes, but for this particular set of parameters, there are only a few which contribute a significant amount of power. Then we can start gridding over parameters. As a first pass, we looked at what happens when we grid in eccentricity and inclination. We looked over a range of inclination from 0 to 80 degrees, a range of eccentricity from 0 to 0.9, and fixed all other parameters. In order to visualize how spectra change as a function of parameters, we can take cross-sections of the parameter space and make 3D color-coded plots. We've termed these Quill plots because of how the spectral structure evolves as parameters are varied. A single row of this plot corresponds to one power spectrum. Not only are these a nice way to visualize spectral trends, but they may inform whether or not we can interpolate spectra as a function of astrophysical parameters, something we hope to look into further. They also allow us to see which frequencies carry the most power as parameters vary, which could be useful for informing numerical waveform generation. Again, we can use these plots to visualize trends, but also to verify Drasco's description of spectral trends. If we compare two Quill plots, one where we fix eccentricity and vary inclination, and one where we fix inclination and vary eccentricity, we see that the plot where eccentricity is varied results in more drastic changes to the spectra. This agrees with Drasco's spectroscopy predictions. You'll also notice that as the parameters transition away from the zero eccentricity equatorial case, there's a sharp break in spectral feature trends. This is something we plan on exploring in the near future with perturbative grids. Going forward, we want to be able to generate these plots using more accurate waveform approximates, like Tucholsky waveforms or even fully relativistic waveforms. Now that we have the code infrastructure in place, we also plan to generate denser grids with more parameters, like black hole spin and SLR, and use Quill plots to identify trends. Ultimately, we want to translate these Quill plots and related data products into something that can be used by astronomers to understand and communicate EMRI physics. Thank you for listening, and thanks to my advisor Shane for the guidance on this project. Here are my references, and please let me know if you have any comments or questions.